Hello student. Today let us discuss about differentiability. So first we'll discuss what is differentiability. So for differentiability we have to consider a function. Suppose you consider a function f and a function f is said to have left derivative at the point x equal to a. That means we have considered a particular point x equal to a, and at that point the function is said to be left derivative if and only if, and if and only if shortly we can denote it by I double f. F is defined in some left neighborhood of x equal to a, and that limit is denoted by what? Limit h tends to 0 minus 0 f of a plus h minus f of a by h exist. You see, you have got this result in class 11 in detail how to get it. Differentiability by definition of ddx we have got in class 11 as what? Limit h tends to 0 f of x plus h minus f of x by h. Okay, and that derivative if I consider left hand side and the right hand side, that is limit h tends to 0, if I consider 0 plus 0 and 0 minus 0. 0 plus 0 means it's a neighborhood of any point which is very near to 0 from the right hand side, and 0 minus 0 means what? It's a point which is slightly less than 0. Okay, and that is your left and right hand derivative. If this particular point if you consider, that is your left hand and right hand derivative. So here you see the value of this limit. This limit means this limit. The value of this limit is called left derivative at x equal to a, because you have considered 0 minus 0. That's why it is left derivative at the point x equal to a, and it is denoted by f dash minus a or by L f dash a or by L f dash a. You see this one. And what is L f dash a? L f dash a is equal to limit h tends to 0 minus 0 f of a plus h minus f of a by h. Similarly, if I consider this limit tends to 0 plus 0, that will call the right derivative. So here you see a function f is said to be right derivative at the point x equal to a if and only if f is defined in some right neighborhood of a, and limit h tends to 0 plus 0 f of a plus h minus f of a by h. This is exist. This limit exists from the right side. You see 0 plus 0. That means 0 plus 0 will be lies on the right side of 0. So if this limit exists, then we call this is right derivative, and the value of this limit is called the right derivative at the point x equal to a, and right derivative is denoted by f dash plus at the point a or r f dash a. That is, you see, what is r f dash a? R f dash a is equal to limit h tends to 0 plus 0 f of a plus h minus f of a by h. So you have seen here that what is right derivative and what is left derivative. Right derivative means we have got limit h tends to 0 plus 0 of this limit, and left derivative means limit h tends to 0 minus 0 value of this limit. Okay, so a function f is said to have a derivative at the point x equal to a if and only if f is defined at some neighborhood of a and this limit exists. Limit h tends to 0 plus 0 f of a plus h minus f of a by h is equal to limit h tends to 0 minus 0 f of a plus h minus f of a by h. If they are equal, it is right derivative equal to left derivative, then we call this limit exist. And after this you see this, the value of this limit is called the derivative at the point x equal to a, and it is denoted by f dash a. And what is f dash a? Limit h tends to 0 f of a plus h minus f of a by h. So simply you remember this is the value of this limit, that is the derivative of f dash a. F dash a, and this limit if it is exist from right and left both the side, then we call the limit exist. From the above definition it follows that derivative of a function at the point x equal to a exists if and only both the left and the right hand derivative exist separately and their values are equal, which is actually similar with the continuity. Continuity we simply consider the left and right hand derivative of fx, left hand right hand limit of fx, but here instead of fx you have to consider that particular limit. What is that? F of a plus h minus f of a by h from left and right. So this is exist and equal, we call the function is differentiable. The derivative of a function f at the point x equal to a is also called differential coefficient of f at the point x equal to a. The function f is said to be differentiable. That means when we call it differentiable, at a point x equal to a if and only if derivative of a function at a exists As I told you earlier, the same thing is repeated here. I have written it. So here you see it is exists, and the process of finding out the derivative is called the differentiable. So we have seen here differentiable at a point x equal to a. At the point x equal to a, it is denoted by this symbol. If this limit exists and their values are equal, both left and right hand derivative of this limit exist and their values are equal, we call differentiable at the particular point x equal to a. So in place of x, we have to write down a. Okay, and this is at any point. If I want to define derivative at any point means suppose at the point x we want to define the definition. A function f is said to have a derivative at any point x if and only if it is defined for some neighborhood of the point x equal to a, and this limit exists. You see, limit h tends to 0, f of x plus h minus fx by h exists. The value of this limit is called derivative of f at the point x equal to a, and is denoted by f dash x. And this f dash x equal to what? Limit h tends to 0, f of x plus h minus fx by h. And if I put x equal to a at a particular point, then this value we will obtain. So hope you understand when we'll call derivative at a point. Now you see, next we have to know a relationship between differentiability and continuity. You remember this is a very important theorem or a relation. The theorem is stated like this: if a function is differentiable at the point x equal to a, it must be continuous at x equal to a. That means if it is given that differentiable, then we can give the conclusion that obviously it will be continuous. Let us prove the result. So first, what is given? It is differentiable. Since f is differentiable function at the point x equal to a, so by definition, what is the conclusion we can give? Limit h tends to 0, f of a plus h minus f of a by h is equal to f dash a. This is by the definition of differentiability. And we have to show it that this is continuous. Hope you remember the definition of continuous. What is continuous? When we'll call the function is continuous at the point x equal to a, if limit x tends to a, fx equal to f of a. So just to get the answer, we have considered this function now, difference of the function, this numerator present, f of a plus a minus f of a, and this can be written as f of a plus h minus f of a by h into h. This remains as it is. H is not equal to 0, then only division is possible. That means we just divide this side by h, and just to cancel or maintain the equality, we multiply it by h, and this step is done just to get the answer. Then to find out this limit, let us take the limit on both sides. Limit of h tends to 0 of this function, limit of this result. Then limit can be separated. Limit of sum or difference can be written as difference of limit. Similarly, product of limit of product can be written as product of limit. So we have separately written this limit with this one, limit with this one, limit with this and this. Now you see here, after this, you see you can just keep it as it is. Limit h tends to 0, and this is independent of h, so it will remains what? F of a, and this is nothing but f dash a. Sorry, it should be a. Okay, f dash a into this is 0, so the value will be equal to 0. So what we have got? Limit h tends to 0, f of a plus h is equal to, because right side 0, if I bring this to the right side, it becomes f of a. Now if I want to find out the general definition of limit, let us substitute this is equal to x. So if I substitute a plus h equal to x, then h will be equal to what? X minus a. So h tends to 0 means x minus a tends to 0, that means x tends to a. So here you see limit h tends to 0, f of x plus h. This one can be written as limit x tends to a, fx, because h tends to 0 become x tends to a, and a plus h, in the place of a plus h, I have substituted x, and that is equal to f of a. And what is the conclusion you can give from here? This is nothing but the definition of continuity at the point x equal to a. So we can give the conclusion that the function is continuous at the point x equal to a. So what we have seen? Since it is differentiable, that's why I can use here. What is this? This is f dash a. This f dash a can be used because of this. This is differentiable, and if it is differentiable, then lastly we have got the conclusion that this is continuous. Now we see second. Let us discuss one more result. That is here the converse of the above theorem is not true. And what is the converse? That means differentiability. We have got differentiability implies continuity, but continuity does not imply differentiability always. The converse of the theorem is may not be true. What is that? That is, a function may be continuous at a point, but it may not be differentiable at that particular point. So if it is not, I had already told you that it is sufficient to give an example. So I have considered the example of fx equal to modulus of x, which is known to you. Modulus of x can be written in this way, in expanded form. Let us examine at a point. At a particular point, let us take it that it is continuous, but it may not be differentiable. So I have considered a simple point at the point x equal to a. So what to do? We have to take the limit x tends to 0 plus 0 and 0 minus 0 separately. So let us find out here the limit x tends to 0 plus 0 fx. And 0 plus 0 fx means what? Greater than 0, so it will be x. Putting the value of x, we get 0. And for 0 minus 0 fx, 0 minus 0 less than 0, function is defined by minus x. Putting the value, we got it 0. So here we have seen that right hand limit is equal to left hand limit. Therefore, limit x tends to a, x tends to 0 fx exists. And what is f0? For equal to 0, it is equal to 0. So 0 is equal to 0, f0 is equal to 0. So we have seen that limit value is equal to function value. Hence, f is continuous at the point x equal to a. That means we have seen here that modulus function is continuous at the point x equal to a. Now at x equal to 0. Now let us consider the differentiability at the point x equal to 0. So your point is 0 now. F dash 0 will be equal to what? In definition, f dash x is what? Limit x tends to 0, f of x plus h minus fx by h. So in the place of x, I have substituted 0 because I want to get the differentiability at the point x equal to 0. So when I put it 0, it will become 0 and this is also 0. So it becomes limit x tends to 0, f of 0 plus h minus f0 by h. 0 plus h can be written as 0, h, f of 0 by h. What is f of h? F of h will be equal to modulus of h, modulus of 0 by h. Now you see, we have got modulus 0 is equal to 0, so this can be written as limit h tends to 0, modulus of h by h. Now here we cannot use the value of h because tends to 0, maybe positive, maybe negative. So it is positive and negative, you have to separate now. So that's why I have separated here right hand derivative. I have considered rf dash x. Rf dash 0 means 0 plus 0, it is 0 plus 0 will be on the right side. So 0 plus 0, this is written, modulus of h by h. For 0 plus 0, modulus h value will be h. H by h is equal to 1, that is equal to 1. Now consider a left hand derivative, that is what? Limit h tends to 0 minus 0, modulus of h by h. And modulus of h can be written as minus h by h, which is equal to minus 1, and that value is equal to minus 1. So we have seen right hand rf dash 0 is equal to lf dash 0. Okay, rf dash is equal to lf dash 0 is not equal to lf dash 0. So what is the conclusion? F is not differentiable at the point x equal to 0. Because to be differentiable, you must have right hand derivative is equal to left hand derivative. Hope you understand this theorem. This is set in exam also. Okay, let us do a problem now. Show that fx equal to x squared is differentiable at the point x equal to 0, 1. It's a question not from your textbook. It's just an extra question I had given here. So let us find out f dash 0. What is f dash 0? F dash 0 by definition it will be equal to limit h tends to 1 plus h minus f of 1 by h. F dash 1 we have to get. So after using this, let us use the value of the function. So fx is defined by x squared. So 1 plus h will be defined by 1 plus h whole square. And f of 1 is equal to 1 square. So I have substituted this function value. After this, let us do the calculation. So 1 plus h whole square can be written as 1, a plus b whole square formula, 1 into 2 into 1 into h plus h square minus 1. This is cancel out. H is coming common, 2 plus h by h. H will be cancel out, and what is left? Limit h tends to 0, 2 plus h. So substituting 0, we got it 2 plus 0 is equal to 2. So we have seen here that the value of f dash 1 is equal to 2. Okay, now let us find out here the differentiability. Let us take the differentiability of the function, this one. The function is defined, in this case you see the just a minute. In this case you see the function is defined by x minus 1 for x less than 2 and twice x minus 3 if x greater than equal to 2. So here you see the limit directly we cannot find out the derivative because for greater than 2 and less than 2 function is defined by 2 different ways. Right? So we have to separately do the left hand derivative and right hand derivative. In the previous case is not required to do because the function is defined only by one way. That's why I have done here directly f dash 2. F dash 2 I have done directly. And then we can substitute the values of 1 plus h also. But if you see here, if I do only f dash 2 here, f dash 2 can be written as limit h tends to 0, 2 plus h minus f2 by h. Now you see 2 plus h. H tends to 0. H tends to 0 means if h greater than 0, then 2 plus h will be greater than 2. Is not it? So 2 plus h will be greater than 2. So 2 plus h will be greater than 2. That's why I have to separate these things. That is 2 plus h. Here I have separated h tends to 0 plus 0 once, and then I will do h tends to 0 minus 0. 0 plus 0, it is on the right side of 0. So r f dash 2. f dash 2. Here you see I have just substituted this one. Now I have to substitute the value of this 2 plus h. That's why I have done this calculation as a rough work. H is greater than 0. 0 plus 0 means greater than 0. So here you see 2. If I add 2 on both sides, 2 plus h is greater than 2 plus 0. That means 2 plus h is greater than 2. Because I need 2 value, that's why I have added 2 on the both sides. Greater than 2 or less than 2. 2 is the critical point. Because of that reason, I have added here 2. So for greater than 2, it is the function is defined by twice x minus 3. So if fx is twice x minus 3, what is f of 2 plus h? 2 into 2 plus h minus 3. Okay, and then f of 2. 2 is equal to 2 is also there. 2 into 2 minus 3. So let us do the calculation after substitution. That is equal to what? 2 into, this is 4 plus twice h minus 3 minus 4 minus plus 3. This is cancel out. 2h by h is cancel out. This is 2, and what is equal to? That value is equal to 2. Now I have to go for LF dash h. LF dash 2. And you see what is LF dash 2? LF dash 2, the limit value is this one, but which one I will prefer? You see, h is now less than 0. H less than 0 means if I add 2 on both sides, 2 plus h less than 2. And for 2 plus h less than 2, the function is defined by x minus 1. So your function is now this one. Fx is x minus 1. So what is your 2 plus h? 2 plus h minus 1. So this is written 2 plus h minus 1. And what is f of 2? It is equal to 2 is defined by this way only. The previous case equal to is defined by 2x minus, just 2x minus 3. So 2 into 2, here what you have to put? 2 into 2 minus 3. Do the calculation, 2 plus h minus 1. And this is 4 minus 3 is equal to 1. Minus 1 plus 1 cancel out. Minus 1 plus 1 minus 2. Minus 2 plus 2 cancel out. H by h is equal to 1. So we have seen the left hand derivative is equal to 2, but the right hand derivative is equal to what? 1. So left hand derivative is not equal to right hand derivative. Therefore, the function is not differentiable at the point x equal to 2. Hope you understand the procedure. Okay, now we'll do one more question. These are extra questions. These questions are not from your NCERT textbook. But this type of questions are required for exam. That's why I have given the solutions. Show that the function fx, x into sine of 1 by x, x not equal to 0, and is defined by 0 for x is equal to 0, is continuous but not differentiable. So let us, at the point x equal to 0. So at the point x equal to 0, let us first take the continuity. Limit h tends to x tends to 0. Tends to 0 means 0 plus 0 and 0 minus 0. And for both of them, it is defined by one way, not equal to 0. So I have substituted, this is not equal to, separately do the limit. So I have just considered substitute a function not equal to 0. It is defined by x into 1 by x. So here you see this limit of product of limit can be written as limit of product. Now I can substitute here, but it is not possible to directly substitute the value of 0 here because it is 1 by 0 is infinity, does not exist. But we know sine function is what? Sine function is a periodic function. It is oscillate between minus 1 and 1. So whatever the value of x we get, always will have the sine theta values between minus 1 and 1. So we can write down here a finite number oscillate between minus 1 and 1 because of this reason. Because you know this sine theta value always lies between minus 1 and 1. So it's a finite value. So here I have written finite values, and 0 into finite value is 0. Okay, now what is f0? f0 is for equal to 0, it is defined by 0. So here we have seen limit h tends to 0, x tends to 0, fx equal to f0. That means f is continuous at the point x equal to 0. Now I have to do differentiability, check for the differentiability. And for differentiability, you see what to do. Limit f dash 0 we have to take. F dash 0 means limit h tends to 0, 0 plus h minus f0 by h. 0 plus h will give you h and f0 by h. Let us now see whether I have to separately write down 0 plus 0 and 0 minus 0 or not. H is, you see, if I take h plus 0, h is 0 tends to 0 plus 0. 0 plus 0 means more than 0. More than 0 is not equal, here you see not equal to 0 function. More than 0 is not equal to 0. And if I take h tends to 0 minus 0, less than 0, for less than 0 also not equal to 0. So don't have to do separately the left and the right hand derivative. That's why I have substituted directly. F of h equal to what? H into sine of 1 by h. F0 is 0 by h. H will be cancelled out. Limit h tends to 0, sine of 1 by h exists. You see, we know this is a finite value, but it is not a fixed value. It is an oscillate between minus 1 and 1. That means we not get a fixed value for this. If I not get a fixed value, that means for slightly more or greater, if I change this value, then it will have different values. That means this does not exist because it is a number oscillate between minus 1 and 1. We know it's a number, finite number, but oscillate means changes between minus 1 and 1. That's why we can give the conclusion that f is not differentiable at the point x equal to 0. Today I stop here. Next video I'll give you the solutions of differentiability questions from exercise 5.2. Thanks for watching.